So in the lab, we made alum crystals, and we did this using a process called recrystallization purification, which is a method that uses solubility to gradually remove substances that you don't want until you get the one that you do. We performed a series of 4 different reactions, the first of which is shown here. This was done by dissolving solid aluminum foil in a solution of KOH to get this black liquid that I drew here. The goal was to get the aluminum ions from the foil dissolved into solution for later reactions, and we made sure that this happened by filtering out all the impurities that were present in the aluminum foil. Next, we added some sulfuric acid to the solution, which ended up forming aluminum hydroxide. This aluminum hydroxide precipitated out of the solution as a solid because it was not soluble in the solution. Next, we needed to dissolve the aluminum hydroxide so that we could free up its aluminum ions. So to do this, we added more sulfuric acid. This is going to increase the interactions between solute and solvent molecules and therefore increase dissolution. And then we heated the solution to raise the temperature. This was going to break the bonds between solute molecules and encourage them to dissolve into the solvent. Next, we took our solution and we stuck it in an ice bath to lower the temperature. Since solubility increases as temperature increases, lowering the temperature would lower the solubility of the alum molecule in the solution so that it precipitates out of it as a solid. Finally, we calculated the correct amount of alum we would need to make a saturated solution. In other words, a solution that contains as much dissolved solute as it can at the given temperature. In the saturated solution, the process of dissolution, where the crystal is dissolving, is at equilibrium with the process of crystallization, where the crystal is growing. We want the crystals to grow, so in order to do that, we have very slow evaporation of the solvent. Over time, this will increase the rate of growth relative to the rate of dissolution as the solvent disappears. Now you might wonder how you could make similar crystals of salt or sodium chloride, and there are multiple ways that you could go about doing this. One is by calculating the amount of salt needed for a saturated solution of the solvent water at a given temperature. You could then extend what's called a seed crystal on the end of a stick or a string into your saturated solution and let the solute evaporate slowly so that crystals form around and off of the seed crystal. Or there's my personal favorite, where you make a supersaturated solution of sodium chloride. Since solubility is greater at higher temperatures, dissolving salt into hot water and then allowing the solution to cool down gives you a solution with a greater amount of solute in it than if the water had been unheated. So after you dissolve the salt into your hot water, you slowly allow the solution to cool down so that crystals form. Both of these methods work for other types of crystals as well, besides alum and sodium chloride. I actually used the supersaturated solution method to make these crystals out of borax a little while ago, so as you can see, it's a pretty effective method. So let's check on the crystals. Oh, well, there aren't any yet. That is because the solvent, which is water, is still evaporating very slowly, so the alum is still pretty well dissolved in it. And it's only been a few days, so hopefully next week there will be some crystals.